Okay, so all right, so in the last class, we were sort of in the middle of chapter 5, and actually, let me see if I can find our summary slide. Yeah, let me start with this guy right here. Copy. Okay. So this is a summary of a lot of the important concepts that we covered in the last class. So we start with the work energy theorem. That is, the net work done on any object is equal to the change in its kinetic energy. And then we saw that there are two types of forces that can do work: conservative forces and non-conservative forces. So the net work done on an object is the work done by all the conservative forces plus the work done by all the non-conservative forces. And then we saw that conservative forces have this property that the work that they do when an object moves between 2 points is independent of the path that the object takes. It only cares about what the initial and final point is. And therefore, I can express the work done by a conservative force as minus the difference of some function that is evaluated at those initial and final points. We give that function a name. We call it the potential energy function. So I can always write the work done by a conservative force as minus the change in the potential energy function as the object moves between those 2 points. And for gravity, we saw that there's a potential energy function, which is mgy. So you just tell me what is the initial and final y coordinates, and I can calculate the work done by gravity. So if I then substitute this guy back up here, then isolate for and then solve for this work done by non-conservative forces, I get that the total work done by all non-conservative forces is the change in the kinetic plus potential energy. And then we give this combination a name. We call it the total mechanical energy of the system is the kinetic plus potential energy. And therefore, this thing on the right here is nothing more than the change in the total mechanical energy of the system. And so I can re-express the work energy theorem as the work done by the non-conservative forces altogether is equal to the change in the energy of the system. And then you have the conservation of total mechanical energy. Whenever this left side is 0, then the change in the energy will be 0, and then we have conservation of energy. And that happens in one of two cases. Either there are no non-conservative forces at all in the problem, then obviously this is just 0, the left side. That is, there's no friction, for example. Or there could be some non-conservative forces, but they don't do any work, like a normal force, for example. So when something is sliding on a surface, on a frictionless surface, the normal force is not a conservative force, but it always just does 0 work. And so therefore you will still have conservation of energy. Any questions on that? So I would just basically memorize this logic. It is a very useful thing that we will talk about. Any questions on that? Okay. So actually, here is a quick quiz. And stare at this slide over here to help you process this. We are told that there's a book that is picked up from the ground. So there's a book sitting on the ground, someone picks it up and they place it on top of a bookshelf and then they just place it there. The question then is, what is the net work done on the book in this process? Is it positive, 0, or negative? All right, so let's see. Let me go to top hat here. The attendance code is 9032. All right, any questions about the question? So here it is. All right, 8 seconds. All right. Well, the correct answer is actually 0. So what is going on over here? So let's unpack this a little bit. The question is asking is, what is the network done on the object? And what is the network done? It is the work done by all the forces acting on it together. So when you're picking up the book from the ground and you place it on the bookshelf in that journey, how many forces are acting on it? Which one? So there's the force that you are lifting it up with. What else is there? Gravity, right? So there are two forces acting. You're doing some work, and gravity is doing some work. The question is not asking how much work you are doing. It's not asking how much work gravity is doing. It's asking what is the network done on the object. And what do we know about the network? The network done on an object is equal to the change in its kinetic energy. So does everyone see why the network done is now 0? What is the kinetic energy of the object when it was on the ground? It's just sitting there.
So would the work be positive if we were trying to find the instant when it was being moved?
Yeah, so the question is, so here's a little bookshelf, right? And that's my little drawing. There's a book here, sitting there, and then someone comes along, and then they place it over here. So the object is at rest when it's on the ground, and then when they lift it up and they put it over here, the object is at rest again. So therefore, its initial kinetic energy is 0, its final kinetic energy is 0. And so therefore, this is the same as the final kinetic energy minus the initial kinetic energy, which is 0 minus 0, which is 0. So the net work done on the object is exactly 0. And the statement then is that there are two forces, as we said. There's the work that you are doing. So let's call that the applied force. You're doing some work in trying to lift this object up. But then there is also the work done by the force of gravity. And together, they add up to 0. Does that make sense? As a follow-up question, let me, it's not a top pack question, but let me just throw it out there to people on Zoom and people on the class. What is the work done by gravity? Is it positive, negative, or 0 in this journey? Negative, right? Because we're the displacement of the object is going up, force of gravity is down. So if I assume that it's moved up in a straight line, then FD cosine theta will be FT cosine 180. Gravity will be doing negative work. And in that same journey, you are going to be applying some force upwards. And so you end up doing positive work. And the statement is that because at the end of the day, it started at rest and it ended up at rest, there was no change in its kinetic energy, the work you do must be exactly opposite of whatever the work gravity did, so that the net work is zero. Any questions on that?
In the middle of that, journey would be possible.
Say it again?
The network in like the middle of when you're moving it would be positive.
It depends on what the kinetic energy is of the object at any given point over there. So you could imagine that you lift it up and then you hold it there for a second, and then you put it on the bookshelf. So again, if you're just holding it up there, initial and final kinetic energy are again zero. So then the network will be zero. But if you're really pushing it up, and then at some point there is some speed that it has, then in that journey there will be some non-zero work done, net work done. Any questions on that? So that is an example of how this slide is super useful. Right, so the question asked you, what is the net work done on the object? The very first equation is giving you something about the net work. It's the change in the kinetic energy. So I look at that and I say, oh, the object started at rest, ended at rest, net work must be zero. Okay. Any questions on that? Okay, so there's one last point about potential energy, which is the idea of reference levels that go into the definition of the potential energy. So when I say that there's some object that has, let's say, a potential energy of mgy, well, that y is some height relative to wherever you're calling y equaling zero, right? There's some reference level, some sort of sea level where you're saying y is zero. And then if I say something has a potential energy of mgy, then that is the potential energy with the convention that your sea level is y equaling zero. So it's in reference to that point. So in other words, let me say it in this way. Here's a book that is sitting, these three books are all the same height, right? They're all the same height. But I could still say that their potential energy, mgy, can have a different number depending on what you call y equaling zero. So if I say that my y equaling zero is the surface of the table here, then the mgy will just refer to this height. But if I say that the y equaling zero is this floor, then the potential energy will be mg times this height. Whereas if I say that the potential energy of y equaling zero is down here, then the potential energy of this object is this height, right? So when I say what is the potential energy of an object, if someone asks you that question, the first thing you should ask them is, well, in reference to what level? Where are you defining your y equaling zero? And so the point is that this is okay as long as you pick some reference level and you stick with it throughout the problem, then you're fine, because if you go back and you notice, what really appears in the physics equations is always the change in the potential energy, right? And so if an object has changed its height by some amount, then the change in the potential energy will be the mgy final minus the mgy initial. That height difference, it doesn't matter where you're calling y equaling zero. It's just whatever height it moved, right? And so therefore what appears is always the difference in the potential energy in all these equations. So therefore your physics is invariant depending on where you call your y equaling zero. But in any given problem, you have to make a choice when you say y equals zero somewhere, and then you have to be consistent with that convention. So a reference level must be specified for the potential energy. That is, the location of where we set the potential energy to zero must be chosen. That is the same as choosing your y equaling zero. And then we come to this picture here. And so again, like I said, this mgy could have different values for the same height, depending on where you're calling y equaling 0. But as long as you pick one height, one reference level and stick with it, then it should be okay. Any questions on that? No, I'm saying in any given problem, pick where your y equaling 0 is. That will then the potential energy of all the objects will be defined relative to that y equaling 0. And then you just stick with that convention. So you could say, for example, here is my y equaling 0.
Apply that to C or B.
I mean, I'm thinking of these as three different situations, but let's imagine that we're looking at this situation A. So my y equaling 0 is the table. So let's say that a little bit later, maybe the book falls, and then like it comes in and it hits the table right here. Let's say it falls down and hits the table. Then if I ask you, well, what is the change in its potential energy? It doesn't matter where I call the y equaling 0. The thing that's going to appear in your definition is this delta y, this difference in the height, right? Because it'll be mgy final minus mgy initial. So it's not going to matter where exactly you set your y equaling to 0. And what appears in all the physical equations is always the change in the potential energy. So that's the statement. So let's see, let's look at an example. So in this example, I'll kind of slow it down and we'll do this problem here. So here we are told that there is a diver of mass m, and he drops from a board 10 meters above the ground. Notice that over here in this picture, they've already drawn a coordinate system. They've already called this ground over here y equaling 0. This is y equaling 5 meters, and the height of the board is 10 meters. So if we work with this coordinate system, we've already chosen our reference level that the mgy of this diver will be 0 when he hits the water, because that's where y equals 0. And then his potential energy up here will be mg times 10 meters. His potential energy at this height will be mg times 5 meters. And on the ground, it'll be 0. Any questions on that? Okay. So in this problem, they say, so this diver kind of just drops from rest, falls to the ground. It says, use the conservation of mechanical energy to find his speed 5 meters above the water's surface. So in other words, this diver is falling down, and in this journey downward, they want to figure out what is the speed of the diver when he's at y equaling 5 meters above the surface of the water. Any questions on that? In chapter 2, what you would do is you would say you draw a free body diagram, or sorry, there'll be constant acceleration, 9.8 meters per second squared. And then you can use one of your kinematic equations and figure out what is the speed of the diver over here if he starts from rest up there. What we're going to do here is we're going to use our energy formalism to answer this question. So the first thing to keep in mind is that in this problem, as the diver falls, the only force acting is the force of gravity. Right, well, again, we're ignoring air resistance and all that. Right, if you draw a free body diagram for this diver, here it is, there's a diver. The only force acting on him will be downwards, mg, and let's say this is your positive y direction. So if that's the only force acting on the diver, gravity is a conservative force. And So the only force acting on the diver is the conservative force. So recall from the work energy theorem that the work done by all the non-conservative forces acting on the object is equal to the change in the total mechanical energy of the object, right? And what we're saying is, since gravity is the only force, there's no other force acting on it, obviously, the work done by the non-conservative forces will be zero because there is no non-conservative force in the problem to talk about. Right? So that means in this situation, the change in the energy is zero. So whatever total mechanical energy the diver had up here, the diver will have exactly the same mechanical energy at y equaling to 5 because there was no non-conservative force acting on him in this journey. So therefore, energy must be conserved. So to write this out more explicitly again, this is saying that 0 is equal to the final energy of the diver minus the initial energy of the diver. And so therefore, you get that the final energy is equal to the initial energy. That is, we have conservation of energy, and we're going to use the conservation of energy to solve for what is the speed of the diver at y equaling to 5 meters. Well, what is the total mechanical energy of the system? It is always equal to the final energy will be the final kinetic energy plus the final gravitational potential energy must be equal to the initial kinetic energy plus the initial gravitational potential energy. Any questions so far? Well, the final kinetic energy is going to be 1/2 m, whatever that v final squared is, and this is the thing that we're trying to find, right? We're trying to find what is v final. And then I have here plus the gravitational potential energy. What is the gravitational potential energy? Well, the diver was initially over here at some initial height. Let's call that y initial, which was 10 meters. They will have energy, potential energy, which is mg y initial, because we've now taken the reference level y equaling 0 to be at the water. So here, let me just say, right, the y initial here is 10 meters. The y final here is 5 meters, right? So the diver starts here, and then at y equaling 5 meters, we want to know what his speed is. And then the same thing on the right. On the right, you will have whatever the initial kinetic energy of the diver is, plus whatever the, oh, sorry, I made the, this should be, this should be y final over here. Is that why some of you were looking puzzled? Right, this is the final energy, so it is the final kinetic energy plus mgy final. This is the initial kinetic energy, and then this will be the initial potential energy, which will be mgy initial. So that's just sort of the general formula, right? We have energy conservation, but now we can go and look specifically as to what is happening in this problem. In this problem, we know that y initial is 10 meters, y final is 5 meters. We know that v initial is 0 because the diver just starts from rest and then falls. And then v final is the thing that we want to find. That is the information that's given to us. Any questions on that? So this means that v final, the v initial here, this will be 0. right? Because V initial here is 0. So the diver starts initially at rest, which means at this moment, the diver has 0 kinetic energy. So that's why this initial kinetic energy is 0. And then everything else is non-zero. Y initial is 10, Y final is 5, V final is what we're trying to solve for. Any questions on that? And so therefore, now we can just kind of be zen about it and go through the math. We have 1/2 mv final squared plus mgy final is equal to mgy initial. And in fact, I can just divide both sides by m, so the mass just goes away. And then you end up with vf squared over 2 is equal to g y initial minus g y final, and therefore you end up with vf squared as being 2g y initial minus y final, and therefore vf is the square root of 2g times y initial minus y final. And we can now plug in the numbers. Right, I can go ahead here. So with this, you end up with V final as being the square root of 2 times 9.8 meters per second squared times Y initial is 10 meters, Y final is 5 meters. And therefore you get V final is, let me just look ahead at what that number is, 9.90 meters per second. Any questions on that?
Sure that last final velocity is correct, because 2 times 5 would be 10 times 9 would be 98, so it would be square root 98.
Correct.
And square root.
And what is square root of 98?
Sorry.
Square root of 98 is, yep, 9.9. Right, so again, just to summarize the logic in this problem is that we are using the conservation of energy because we notice that when the diver is falling, the only forces acting on him are conservative. So therefore, the whatever initial energy he had when he jumped off must be equal to the final energy at 5 meters above the ground. And then we just apply this energy conservation and solve for the variable that we're interested in, which in this case was the final speed. Any questions on that? Now there's a part B that says find the speed of this diver as he hits the water. And again, the logic is the same. So if I go down here to part B, which is find speed when diver hits the water. Again, I can use energy conservation. E final has to equal E initial, where again, E initial I can just think of as him jumping off the springboard. And when he hits the water, I will get that this is 1/2 mv final squared. What is the potential energy when he hits the water? It's going to be 0 because y is 0, right? So this will be, I'll just say here plus mgy final. Let me just write this out. is 1/2 mv initial squared plus mgy initial. Over here, what's going to happen is when he hits the water, this will be 0 because yf is 0 at the water. And over here, this will be 0 since at the springboard, he drops from rest, v initial is 0. So those two terms go away. And so then you just get this very simple result that 1/2 mv final squared is equal to mgy initial. And again, the statement of this equation is that all the initial gravitational potential energy that the diver had when he was standing on the springboard has now been converted into kinetic energy when he hits the water. The total energy is the same, but the form of the energy has been converted from potential energy to kinetic energy. And again, the m cancels out on both sides. And you can then solve for your v final. Squared is 2gy initial, and therefore v final is the square root of 2gy initial, which is the square root of 2 times 9.8 times 5, all meters per second. And that is, what does that come to? 14 meters per second. Oops. So this is an example of how we can use energy conservation to solve this problem. Yep. Question?
Y initial?
Oh, sorry, this should be 10. Yeah, you're right. Oh, this is 10. 10. Yep. This is the start of the springboard. Yeah, so let me make that very explicit here. Right, y initial is 10 meters per second. Y final here is 0. And v initial was 0. Any questions on that? Okay. All right, so here is, have you guys ever seen that demonstration of someone has a pendulum up on their face and then release it? So we're gonna try and unpack that, the physics of that. So in order to do that, let's do the following quick quiz. So here we're told that a person lifts an object of mass 15 kilograms. So this could be like the pendulum that you're lifting off the floor. It's 15 kilograms off the floor and holds it a height of 1 meter above the floor. How many joules of work were done by that person? So now notice, unlike the bookshelf example, it is not asking what is the net work done on it. The net work done on it is 0 because you pick it up. It's at rest. You hold it up 1 meter. It's also at rest. The net work done on it is 0. But it is asking what is the work done by the person lifting it up by 1 meter. And to give you a little head start in trying to attack this problem, again, I will remind you that the work energy theorem says that the net work done on an object is equal to the change in its kinetic energy, which in this case is 0, because this person has lifted the pendulum that was at rest on the ground, and then they hold it up 1 meter above. Again, it's at rest. So the net work done is 0, which means that the net work done on it is 0, but the net work done on the object is the work that you do, the person lifting it up, plus the work done by gravity, and that has to equal 0. And the thing they're asking you to figure out is what is the work that you do and recall that the work done by gravity is just minus the change in the gravitational potential energy of the object as it is lifted from the ground where it was at y equaling 0 to some height where its y is 1 meter, and that has to equal 0, and therefore the work you do is simply the change in the gravitational potential energy of the object. Any questions about that? So with that in mind, let's see if we can do this top hat question. Any questions about this? All right, so, and again, feel free to chat with your neighbor if you need to. Oh, I guess it's not a top hat question. Sorry, my mistake. Okay, so we're just gonna do it. So yeah, let's just go ahead and do this. Anyone have an answer for an extra gold star? Yeah, what'd you say? 147 joules is indeed correct. So this is saying that this is mgy final minus mgy initial. That is the same as mg times y final minus y initial. If you're lifting it up by 1 meter, then you are getting this to be basically mg times 1 meter. So this is like 15 kilograms times 9.8 meters per second squared times 1 meter. We lifted it up by 1 meter. And so this gives us and so therefore you get that the work done by you is about 147 joules. I'm going to show you a YouTube video. And so that prof is going to say that this is roughly 150 joules. Any questions on that? Okay, so I think this is the quick quiz that I'm going to show you. So here, this woman releases this pendulum that is near her face. She just releases it from rest. It's going to swing out, and then it's going to come back. And the question is, will she be in danger of being hit as this bowling ball comes back at her? So think about energy conservation. Also think about what your gut feeling is. And let's see if we can answer that question. Oh, did I not make that a quiz either? Okay. Or did I just skip over it? Oh, okay. All right, I guess I did not make that a question either. So the answer is no, she's going to be okay. And let me just show you real quick on YouTube a video of it. Let me go here and do, what's that thing? I'm not sure if I've shown you videos of this prof before. 801. So right here.
Today, we will talk exclusively about work and energy. First, let's do a one-dimensional case. the work that a force is doing to kill.
Discover fresh new tracks and new music videos every Friday on YouTube Music's release playlist.
They use these devices, they're called a wrecker ball. They use them to demolish buildings. You lift up a very heavy object, even heavier than this, and then you let it go, you swing it, thereby converting gravitational potential energy into kinetic energy, and that way you can demolish a building. You just let it hit, and it breaks a building. And that's the whole idea of wrecking. So you are using then the conversion of gravitational potential energy to kinetic energy. Now, I am such a strong believer of the conservation of mechanical energy that I am willing to put my life on the line. If I release that bob from a certain height, then that bob can never come back to a point where the height is any larger. If I release it from this height and it swings, then when it reaches here, it could not be higher. There is a conversion from gravitational potential energy to kinetic energy back to gravitational potential energy, and it will come to a stop here. And when it swings back, it should not be able to reach any higher, provided that I do not give this object an initial speed when I stand here. I trust the conservation of mechanical energy for 100%. I may not trust myself. I'm going to release this object, and I hope I will be able to do it at 0 speed, so that when it comes back, it may touch my chin, but it may not crush my chin.
I'm just going to interrupt here for 1 second and connect it to the calculation that we just did. So what we just said is that right now when he's holding it up at his face, he has lifted it about 1 meter above the ground. So that thing has 150 joules of energy stored in that thing. And so it has a lot of energy. And so when he releases it, and when it's at its lowest point, it'll have a lot of kinetic energy. And so the question is, when it comes back, because of the conservation of energy, if it's back at the same height, that means it's going to have the same gravitational potential energy it had before. And if its initial kinetic energy was 0, then when it comes back, it will also have 0 kinetic energy, and therefore he will be okay. So let me continue with this.
I want you to be extremely quiet, because this is no joke. If I don't succeed in giving it 0 speed, then this will be my last lecture. I will close my eyes. I don't want to see this. So please be very quiet. I almost didn't sleep all night. 3, 2, 1, 0. Physics works.
All right, that's conservation of energy. I will just say, I probably won't volunteer myself for that because I don't trust the engineers. I trust the physics. I just worry that the hook will come off the ceiling or something, and then we're toast. But all right, I'll see you guys next week.